look at this first one. So it's prom time. The senior class has 220 females and 180 males. 2 seniors will be randomly selected to get a free prom ticket.
Is this for, or you made this?
I made this up. All right. What's the probability that the first senior we would select is going to be a female? Okay. So let's just think about that. How many females do we have? 220. Helps if I got a pen. I got 220. How many total students do I have? 400. If I add those together, okay, I'd have 400 total students. All right. And so we could add those together, and that would give me 0.55. Okay, so 55% chance. That's not terrible. All right, a little better than half. Okay, so then let's imagine that a girl or a female actually won the first drawing and is ineligible to win the second ticket. Okay, what does that do to the number of females that I now have available?
It goes down one.
It goes down 1, right? It would leave me with 219. And what about my total? My total would go to 399. Okay, because I've already used one girl and she can't get it again, right? So I'll pull her out. So what's the probability that the second winner is a male, given that the first winner was female? Okay, given that the first winner was a female. So let's take a look at this. This is a little bit different. Okay. So if we look for the probability that the second winner is a male, given that the first is a female, what was our probability that the first was a female? 0.55. Okay. And then the probability that the second winner is a male. So how many males do we have left? 180 out of 399. So we get this weird number, all right, but we divide those, and what do we end up with? Okay, 0.45, right? So a little conditional probability, and also looking at what happens if we have some what are called dependent events, right? If I'm going to leave that ticket out, all right, that reduces the number of people that I can choose from. It changes my total and all the good things going on, okay? So what we're going to talk about today is using what's called the multiplication rule. We've been doing that already for things that are independent. All right, things that kind of stand alone, they don't depend on each other. We're going to talk about the probability of finding at least one, okay? And that's a new kind of rule. We will use it's kind of a combination of the complement rule, where we subtract from 1, and the multiplication rule. So I'll show you that. And then we'll talk about when's it appropriate to use that multiplication rule. So knowing when I need to do it versus just, you know, when do I multiply, when do I add, all the good things, okay? So take a look at your activity sheet here. It says, can we predict snow days and traffic jams? Okay. I don't know if you've been on Nashville Pike after 3 o'clock, the road in front of Walmart, any day of the week, it is always a traffic jam. All right. It's terrible. There's so much traffic. But a local news station recently added a snow day calculator and a traffic jam calculator to their website. Okay. So what they've given me up there is a snow day calculator. So I want the probability that it's going to snow on Thursday. It's 0.7, okay? It gives it to me right there in the chart. The probability that it's going to snow on Thursday is 0.7. How could I interpret that? What does that mean?
70%.
Yep. If we converted it to a percentage, it'd be a 70% chance of snow. Okay. And then what about the probability that we'd get a snow day on Friday? 6, all right? And that would mean we have a 60% chance of snow. All right, so just reading the chart there, okay? Now, are the events Thursday snow day and Friday snow day independent, meaning they have no impact on each other? What do you think? Right. Right. I say they definitely would have an impact on each other, right? Because if it snows on Thursday and I got a higher chance on Thursday and I'm out of school, okay, then chances are better that I wouldn't go on Friday as well, okay? But if I have no chance for snow on Thursday, then am I probably going to get a snow day on Friday? No. Okay, so they're not independent. Okay. So we would say no. A snow day on Thursday increases my chance of a snow day on Friday. Okay. All right, so the next thing it asked me for is what's the probability of a snow day on Thursday and a snow day on Friday? Usually when we do and probabilities, what do we do?
Add, right?
No, we multiply, okay? It's the end one. So we would usually multiply. But because they depend on each other, we can't multiply here, all right? So it's a little different situation. So we can't multiply because they're not independent. Okay, so this is what comes in with that learning target 3, all right? If we've got two things that depend on each other, then we really can't multiply them, all right? They're not independent. Okay, so that's snow days. Snow days are going to affect when I get another snow day, but let's talk about traffic jams, okay? So what's the probability that I get a traffic jam on Monday? 0.4. Okay, so there's a 40% chance of a traffic jam. Okay, what's my probability of a traffic jam on Friday? 0.7. So again, a 70% chance of a traffic jam. Okay. So let's think, are those two things independent? Does the fact that I have a traffic jam on Monday impact if I'm going to have a traffic jam on Friday? No. Okay. So really, those are just days. Why do you think it's higher on Friday than on Monday?
It's the weekend.
It's the weekend. Everybody's out. All right. So it makes sense that it's higher on Fridays. Okay. So are they independent? We would say yes. Okay. The Monday traffic jam has no impact. Has no impact on Friday. All right, has no impact on Friday. Right? So with that being said, these are independent events, okay? They're independent. And when we have independent events, we can multiply for the probability. All right? So when I look at 8, the probability that we'd have a traffic jam on Monday and a traffic jam on Friday, well, my Monday probability was 0.4. My Friday probability was 0.7. We just multiply them together. So the probability that I'd get a traffic jam on both would be 0.28. All right, so just multiply. Okay, how do you think we would do the probability for a traffic jam every day of the work week? Multiply them all. Okay, they're all independent, so we would just multiply them all. 0.4, 0.2, 0.3, 0.5, and 0.7. We would just multiply them all. Okay. I think you get 0.0084. Okay, when you multiply them all together. Now, this one's interesting, number 10, because we've got this chart here. All that it tells me is about how I might have a traffic jam. Blah, sure. But we want to find the probability that I would have no traffic jams. Okay, so let's think about that. If on Monday it's 0.4 that I will, what would be the probability that I wouldn't on Monday? 0.6. Okay, if the probability on Tuesday is 0.2 that I will, what would be the probability that I won't? 0.8. How are you getting that, by the way?
Minus it from 1.
Subtracting it from 1. So on Wednesday, probability that I will is 0.3. Probability that I won't, 0.7. On Thursday, probability that I will, 0.5. So probability that I won't is 0.5. And then on Friday, 0.7 that I will, so 0.3 that I won't. Okay? And so that gives me 0.0504. Okay? So does everybody understand where I got those numbers? Okay? And this chart was that I will, and then if I won't, I subtract it from 1. Okay? So 0.6, 0.8, etc. Okay? Now, this is interesting. What is the complement of at least one traffic jam this week? What does complement mean in probability? Means not, right? So what would be the complement of at least one? No traffic jams. Okay? So when we talk about the complement, it's the no. Okay? No traffic jams. So here's a probability we want to find. Okay? We want the probability of at least one traffic jam this week. Okay? Well, I know the complement is none. Okay? And I also found the probability of none is right here. Okay? So if I do the complement, I should get, okay, at least one traffic jam. So we're going to do the probability. We're going to do 1 minus the probability of no traffic jam. So we're kind of using the complement in reverse. All right, so 1 minus no traffic jams, 0.0504. So we're going to subtract it. Okay, it's 1 minus no. And so that would give me 0.9496. So we're pretty much guaranteed to have a traffic jam at least once. Okay, and that's referred to as the probability of at least one. We're going to write that down formally in just a second. Okay, probability of at least one is always equal to 1 minus the probability of none. Okay, so whatever event you're talking about, you find the probability of it not happening and subtract it from 1. Right? So the main thing we're going to do today is kind of complement rules, subtracting from 1 to get the numbers we need. We're going to multiply our probabilities if they're independent, all right? And then this probability of at least 1. Those are the main ideas from today, okay? So flip it over to the back and let's just kind of organize our information, all right? We're going to do a few problems and then we'll be good to go. Oh, about dropped my iPad. You see me? Woo, caught it. Woo! That could have been really bad. I sure ain't got no $400, $500 to fix it. Okay. All right, here we go. Okay. Our learning target 1. Right. So when I have independent events, okay, the probability of A and B, we're just going to multiply them. Okay, so probability of A times the probability of B. If we have independent events, that's what we are going to do. Okay. And then learning target, move that. Learning target 2 was the probability of at least 1. We do 1 minus the probability of none. Okay. And those are our main ideas for today, and that's what we're going to work on. Yep. Those are the 2 things we're going to need today. All right, so I do want to kind of walk through these examples and then do the extra ones that I have just so that we're good once you get the practice. I think there's just 3 or 4 questions today. It's not long. And they're a lot easier than some of the last ones that we've done. Okay. So a first trimester screen is a test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a positive result. Assume that the test results for individual women are independent. So it tells me up front that they're independent, okay? So 5% get a positive result. What percent will get a negative result? 95. Okay, so that's good to know. All right, and I just picked that out just from what they said. 5% get a positive result, 95% are going to get a negative. Okay, so it says, suppose that 2 completely unrelated women are having normal pregnancies. Devondra and Miranda are given the screen test. What's the probability that Devondra gets a positive result and Miranda gets a negative result? Okay, so let's start with Devondra. If she's going to get a positive result, what would her probability be as a decimal? 0.05. Okay. Miranda is going to get a negative result. So what would her probability be? 0.95. Okay. And then we just multiply those 2 together. And their probability is 0.0475. So we just multiply. Okay. So they tell us they're independent, so we can multiply. Okay, now let's look at this next one. This is where it gets interesting. Okay. So it says, if 100 unrelated women with normal pregnancies are tested with the first trimester screen, what's the probability that at least one woman will receive a positive? Okay. So what they want me to do is this probability. Probability at least one positive. Okay. To do that, that means I've got to do 1 minus the probability of no positives, right? Now, what makes this one tricky, okay? What makes this one tricky is how many women are we talking about here? 100, okay? We're talking about 100 people. So we've got kind of like 100 probabilities multiplied together, okay? Which is weird, right? So let's start with the no positive, okay? What's the probability that it's not positive? So that makes it negative, okay? And if there's 100 women, I'd need to multiply 100 of those together over time, okay? Have you got time to type that in 100 times? No. Does anybody know a shorthand way in math where we do repeated multiplication? An exponent, yep. All right, we got 100 of them. All right, I got 100 of them. There's 100 women that I need to take that negative for and multiply them together. And then once I get my answer, I subtract it for 1, or you can type it in just like that. Okay, so 1 minus 0.95 to the 100th. See if you get 0.994. Okay? So we got to think, if they tell me how many people, we're going to take that probability and raise it to that power. Okay? So let's look at a couple more examples, and then we're going to be good to go. Okay? So just making sure we understand how this works. Okay? Challenge or disaster. Have y'all watched that special on Netflix, that documentary? It's really good. I was actually at home on a snow day when this happened in school. I was in 2nd grade and watched it happen live. Okay? But anyway, so it's all about the O-rings and all this stuff, right? So it comes in here, and I'm going to kind of sort through the information. But it says, experts estimated that the probability that an O-ring would function properly was 0.977. Okay? So that it would function the way it was supposed to was 0.977. Okay? What would be the probability then that it would not function? How would I get it? Yeah, 1 minus 0.977. Okay, so I don't know if we're going to need that, but that's how we do it. Okay, so now it asks me, assume that them succeeding or failing is independent. Okay, that it is independent. So it says find the probability that the shuttle would launch safely. Oh, go get you some lunch. We'll do this when we get back. No, sorry.